So, in the previous thing we have seen that power unit system. Now, we will come for that method of voltage control, right. So, the methods for voltage control are the use of one is the tap changing transformer, then regulating transformer or booster transformer, shunt capacitor, series capacitor and the fax devices, right. So, in this course we will not discuss about fax devices, right, because it is a very big topic. So, we will not discuss, but we will discuss on tap changing transformer, regulators or boosters, shunt capacitors and series capacitors, just some ideas you will get, right. Now, tap changing transformers, right, that main purpose of our power or distribution transformer basically to transform electrical energy from one voltage level to another voltage level, right. So, practically all power and many distribution transformer, they have the have the taps for changing the trans ratio. So, voltage magnitude is altered by changing the your tap setting and affect the distribution of VAR, that is volt amperes, and may be used to control the flow of reactive power, right. That is for the tap changing transformer. So, basically there are two types of tap changing transformer. One is that offload tap changing transformers, another is the tap changing under load TCUL transformers, right. So, two types of your tap changing transformer. Offload means you have to disconnect the load from the transformer, then you have to change the tap, and another is tap changing under load transformer, that means online you can change the tap, right. So, some schematic diagram, right, some schematic diagram, the offload tap changing transformer requires the disconnection of the transformer from the supply or when the tap setting is to be changed, right, you have to disconnect the transformer from the supply, right. So, this is figure 21, this is actually figure 21, it gives the connection of load tap changing transformer, right. So, in this case there are 4 taps, this side 2 taps, this side 2 taps and a switching mechanism is there. If your this thing that if you want to change the tap from this side to that side, there are 4 taps are there, right, that is why a switch is shown. So, in the other way basically we are reducing the number of turns, right. So, this is primary side and this is your secondary side. If your switch position is here, that is full voltage is applied to that, otherwise the voltage thing your what you call, if it is coming here means that voltage will reduce to this side, right. Similar arrangement is shown here also, right. So, this is your offload tap changing transformer, that means you have to make it offline. Now, next is the TCUL, right, that is tap changing under load, right, is used when changes in turn ratio may be frequent, that means when you want to change the tap ratio very frequently. This is not very frequently, because every time you have to switch on or switch off, right. So, it is not very frequently, but tap changing under load when it is necessary that you have to change the tap very frequently, that is why it is at that time you have to do it online, right. So, it can change while the power is connected to the transformer. Now, this is actually a typical your TCUL connection, right, that is that tap changing or on load tap changing transformers. This is the connection shown when it is your what you call it is when the voltage is maximum. This is figure 22, this is voltage is maximum, this is the line and this is the neutral. These are all connections have been made such that tap can be changed. So, several taps may be there. Generally in a transformer, power transformer, you will find that tap changing may start from your 0.625% to your what you call that plus minus 10%, right. So, one side if it is 0.625 your percent if you take, then lowering or higher side total taps will be maybe 32, right. I mean voltage can vary from 0.9 to your what you call that 1.1, right. but it depends on the design. So, in this case this diagram, this is your line to neutral. Now, this is for the maximum voltage. Now, if we want to, you have to make it on, basically it is online. In that case what will happen, that this is one selector switch, this P1, this is another selector switch, right. And what will happen here, also one connection is there and A1 and another thing is there. What one can do is this, I am not showing it again, this thing, just listen. This one you can open, this one you can open, right. Once you open it, bring the selector switch to the next position, that means here, right, and after that you connect it to A1, that means its position is changed, right, its position is changed. That is why to change the value of the following operation are required: one, open A1, you open this one, right, move selector switch P1 to the next control, that means from here to here, from here to here, right, and then again you close A1. Similarly, from this side also your, what you do, open A2, similar operation, open A2, right. Once is A2, then move selector switch to the next switch, that means you bring it here, right, and again you close A2. This way your voltage level will change, right. So, arrangement I am not showing you again, redrawing all this. So, all steps, that is why I have written that you have to first open this one, right, and then move this P1 to your, what you call, this position, then again you close A1. Similarly, this one you open it, move it here and then again you close it. This way your trans ratio can be changed. So, these are the tap settings, and this is the winding, this is the winding, right, and this is selector switch, this is selector switch. So, this is actually on load tap changing transformer schematic diagram, right. Only for this course is only this understanding that how actually it operates, right. Next is, these operations are required for one change in tap position, right. So, step down units usually have TCL in the low voltage winding. Low voltage side, for actually step down units usually have TCL, that is on the low voltage side, and the de-energized taps in the high voltage side. So, now to little bit for further understanding, you consider this operation of a radial transmission line. Just for the purpose of understanding, we have taken it your radial transmission line, right, with the tap changing transformer on both sides, this side and this side. This is sending end side and this side receiving end side, and this is one node is marked, that is bus bar is marked, or node whatever you say 1, and this side it is 2, right. This is sending end and this is the receiving end, right. And so, actually its objective is to find out the tap changing ratios required to completely compensate for the voltage drop in the line, right. So, you have to find out TS, TR both, though this is 1:TS, and when you look this transformer, you should look from this side. So, it is 1:TR, but this side it is written from if I assume this is primary, this is secondary to primary. So, TR is to 1, basically 1:TR, this side also 1:TR, and this is the line impedance, Z is equal to R plus Jx, and this is the sending end voltage and this is the receiving end voltage. This is a radial transmission line, right. Next, as you know, later we will see after this after all these voltage control methods, later we will see for transmission system. Now, this is your that take receiving end voltage as phasor diagram, that is a voltage phasor diagram. You take, this is your reference voltage, right, and take current through this is lagging, suppose this is the current through this is lagging current phi, right, and then this voltage is your IR, the IR drop, right, and 90° with this is J into Ix, and you complete the phasor diagram. This is sending end voltage, and angle between sending end voltage and receiving end voltage is delta, and current I is lagging from receiving end voltage, that by an angle phi, right. So, this now that this is phi, this is angle phi. So, this angle is 90°. So, this angle is also phi, right. Therefore, this portion AB portion is equal to magnitude I R cos phi. So, I R cos phi, actually it is better if I put that your what you call this IR, the if I put it magnitude, then things will be better. So, if I put magnitude IR, right, and this side actually your JIX, if I put your magnitude I into that your JX, right. So, that way your this is your what you call this AB is equal to magnitude IR cos phi, right, and similarly this BC is equal to ED is equal to your, this is your IX. So, IX sin phi, right. Therefore, sending end voltage, you make the projection on it, you know it. So, magnitude Vs cosine delta is equal to VR, this is the receiving end, plus AB, that is your IR cos phi, I is the magnitude of the current, plus BC, that is magnitude IX sin phi. So, this is say equation 34, right. But this phase angle delta between your sending end and receiving end is very your negligible, very small, right. So, usually delta we can take it say as approximately as 0, right. That means that equation 34, that means this equation 34 can be written as, if delta, here it is delta is equal to 0 you put. So, it is cos 0 1, right. So, magnitude of Vs is equal to magnitude of VR plus magnitude IR cos phi plus magnitude IX sin phi, this is equation 35, right. Now, we can write P is equal to magnitude VR I cos phi, this is power equation 36, and Q is equal to magnitude VR magnitude I sin phi, that is 37, right. Now, from equation 36, from this equation you can write magnitude I cos phi is equal to P upon magnitude VR, and from this equation that magnitude I sin phi is equal to Q upon VR, this is equation 39. Now, this magnitude I cos phi and magnitude I sin phi you substitute in equation 34, you substitute, right. If you substitute, then what you will get? You will get magnitude of, that is I have written using equation 35, 30 and 38 and 39, you will get magnitude of Vs equal to magnitude of VR plus PR plus Qx upon magnitude of VR, right. Now, if you come to this diagram, right, come to this diagram. Now, this diagram your V1, this diagram, that is figure 23, V1 upon Vs, it is ratio is 1 is to Ts. So, 1 is to T, sorry, it is, that means 1 by Ts, say rather than this thing 1 by Ts, that means Vs is equal to Ts into V1 this side. Similarly, if you come to the receiving end side, this side, it will be V2 by VR is equal to 1 by TR, that means VR is equal to your TR into V2, right. So, that means one is VR is equal to TR into V2 and another is your V2, another is Vs is equal to Ts into V1. That means, if you actually it is magnitude wise you take. So, this is magnitude. So, you take all magnitude, that is better, right, because we use only magnitude. So, this one is equal to your this thing. So, magnitude Vs is equal to Ts into V1 and magnitude VR is equal to TR your into TR into magnitude V2, right. So, this Vs and VR magnitude you substitute in this equation. This equation we are substituting that magnitude Vs is equal to Ts into V1 is equal to TR into magnitude V2 plus this PR plus Qx divided by VR is equal to magnitude of V2 into TR. This is equation 41. Now, from this equation you can write Ts is equal to 1 upon magnitude V1 magnitude of V1 in bracket TR magnitude V2 plus this term, right. Now, we will assume one thing, we assume here that the product of Ts and TR is unity, right. This will assume, that is Ts into TR is equal to 1, right. So, as this ensures that the overall voltage level remains the same order and that the minimum range of taps on both transformer is used. So, this is the condition we will put, right, Ts Tr is equal to 1. Therefore, what we will do, we will substitute Tr is equal to 1 upon Ts in this equation, because we want to find out that what will be the expression for Ts, right. That means, if you substitute in this equation, that is in this equation you substitute that Tr is equal to 1 upon Ts, you substitute here. If you do so, that is we are writing here for Tr is equal to 1 upon Ts in equation 42, and you solve it, you will get Ts is equal to magnitude V2 upon V1 back into 1 minus Pr plus Qx upon magnitude V1 V2 to the power minus 1, that means this is 1 upon that actually, right, to the power minus 1 bracket close, then to the power half, right. This is equation 43. So, this is that if you know Ts, then you can find out Tr also, because Tr is equal to 1 upon Ts, because we have assumed that Ts Tr is equal to 1, right, such that both side taps are used. Now, we will take an example, right. So, the example is a 3-phase transmission line. So, before giving to the example, that little bit we have some ideas regarding tap changing transformer, and this expression of to find out the tap ratio. One side either Ts or Tr, any side you find it out. So, from that Tr and to Ts 1, from that you can get the tap ratios. Now, take one example. So, in this case, a 3-phase transmission line is feeding from a 13.8 slash 220 kV transformer at its secondary end, right, sending end rather, sorry, sending end. The line is supplying 105 MVA 0.8 power factor lagging load through a step down transformer of 220 by 13.8 kV. Total impedance of the line and transformer at 220 kV is 20 plus j 120 ohm. The sending end transformer is energized from a 13.8 kV supply. Find out the tap setting for each transformer to maintain the voltage at the load at 13.8 kV, right. Now, this is a simple problem. This is a simple problem. Now, it is the line is supplying your 105 MVA at 0.8 power factor lag. So, it is a 3-phase. So, P is equal to 1 upon 3 into 105 and multiplied by power factor 0.8. So, it is 28 megawatt, right. Similarly, actually when you draw the phasor diagram of this equation P, Q, Vs, Vr, that Vs, Vr all are per phase quantity. So, it is not a line to line quantity. Vs and Vr actually it is a per phase voltage, right, line to neutral, right, and at that time P and Q also you have to find out that per phase, that is why it is divided by 3, right, and Vs, Vr magnitude also per phase basis. So, that is 28 megawatt and Q is equal to cos phi 0.8. So, sin phi is 0.6. So, 21 megavar. The source and the load phase voltage referred to the high voltage side are V1 magnitude is equal to magnitude V2 220 upon root 3. So, all line to line you convert it to per phase voltage, that is 127.017 kilovolt, right. Now, using equation 43, right. So, same equation, use this formula, you know R and X, you know that V1 magnitude V1 is equal to magnitude V2 here. So, magnitude V2 upon V1 ratio is 1, because these two are equal, right. R is given 24 ohm, X is given 120 ohm, P and Q all are known. So, you substitute in this expression all this, right. So, in this case Ts it is ratio 1 into whatever it is 1 minus all this thing to the power minus 1 and to the power half. So, Ts comes actually 1.11. Therefore, Tr 1 upon Ts is equal to it will come 0.90, right. So, these two are tap settings. Now, one more example. So, another one is, so this is understandable, these things are very simple. So, directly you can apply, right. Similarly, example, take another example, example 9. Determine the transformer tap ratios when the receiving end voltage is equal to the sending end voltage. The high voltage line operates at 220 kV and transmit 80 megawatt at 0.8 power factor lag, and the impedance of the line is 40 plus j 140 ohm. Assume Ts Tr is equal to 1. Even it is not mentioned, that you have to assume that Ts into Tr is equal to 1. So, here just taken almost similar type of example. So, that is using equation 43, this is the formula. V2 is equal to magnitude, of course, V1 220 upon root 3 127.017 kV, and magnitude V2 upon V1 is 1. P is equal to 1/3, again per phase basis. So, 21.33 megawatt cos 5.8. Q is equal to 1/3 80 into sin 5.6. So, 16 megawatt, R 40 ohm, X 140 ohm. So, put all these things, you will get again Ts is equal to 1.11 and Tr is equal to 1 upon Ts, that is 0.90. This is the tap ratio. These two simple example we have taken, right. So, this is for the tap changing transformer, right. Now, next is that booster transformer or regulating transformer. In this case, this booster transformer or regulating transformer are these are this thing what you call, it is same thing, sometimes we call regulating transformer, sometimes we call booster transformers. These are actually used to change the voltage magnitude and phase angle, right, at an intermediate point in a line rather than at the ends, right. So, as with the tap changing transformer, what we do? We make it either this sending end side or receiving end side, right, or the system may not warrant the expense of tap changing, but in this case we can put it in the somewhere intermediate position of the line. So, one is voltage magnitude can be controlled, phase angle also can be controlled. So, figure 25 I will come to that, shows the connection of a booster transformer for phase A, right. So, this is your booster transformer connection, right. This is say only phase A we are considering, we are taking line to neutral. So, this voltage is VAN, right, and this is the exciting transformers, right. So, suppose two switch position is there here, this is actually, this is you make S1 say and this is say S2, right, and this is exciting transformer, right. Now, if you come here, right, the secondary of the exciting transformer is tapped and the voltage obtained from it is applied to the primary of the series transformer. That means, this is actually tap position, this is tap position, this is one connection is given, right. For example, another transformer is there called series transformer, is other winding is in series with the phase A line, right. So, this is series transformer and this is exciting transformer. With this thing, here also some voltage is impressed here and automatically voltage will be impressed here, right. Therefore, this VAN dash, this side voltage will be VAN plus delta VAN, right. This is equation 44 I have marked. So, this is the output voltage, right. So, if connection is like this, then this voltage will be added, right. Now, if you interchange this position of S1 and S2, right, then what will happen? This will be a subtraction, right. If you make the position here and this one you will, if you make it here, right, I mean if you interchange the position, then what will happen? That S1 S2 interchange, then what will happen? That it will become it will minus, at that time this voltage will be less than this one, right. So, this way you can go for controlling the your what you call, this is called in phase booster, right, because the voltage are in phase in this case, right. So, this is that your connection, this is that VAN, this is exciting transformer, you have the tap connections are shown, and this is that this output of this is connected to the one series transformer this side, other winding is in series with that phase A, such that voltage can be added or can be subtracted, right, they are in phase, right. So, voltage magnitude can be added. So, this type of booster transformer is called an in phase booster, because the voltage are in phase. So, VAN dash can be adjusted by, I told you, by changing the taps of excitation transformer. The polarity of the voltage across the series transformer can be made reverse by changing the switch position, I told you, from S2 to S1 such that VAN dash is less than your less than your Vn, right. So, this delta Vn, it can be made negative, it can be made negative also if you interchange the position, right. So, this is actually your what you call that your booster or regulating transformer. Now, another thing is that your phase angle control, right. So, booster transformer are also used to control the voltage phase angle. So, a typical arrangement for phase of a booster transformer is shown, right. I mean, this is a booster transformer. Now, in this case, for phase A we are taking line to neutral Van, right. This is A dash N dash Vn dash the output. Now, here this is exciting transformer, this is series transformer, but this is BC, voltage is BC, that your phase BC, VBC, right, plus minus. Now, here also tap settings are there, here also there, switch S1 S2 is there, this series transformer is there. So, this side that we in the phase A, the delta VBC, that voltage will be added, right. So, in that case, so what will happen, the equation will be Van dash is equal to your Van plus your what you call delta VBC, right. That means, I mean, I just see once again that this is phase A, we are taking considering phase A line to neutral voltage, we take other two phases VBC and one exciting transformer is there. From that, these are the tap setting, and this is shown only 2 taps for is showing here, right. And this and output of this is here, it is series transformer, one side of this winding, that voltage is impressed, other winding is in series with the phase A, such that Van dash is equal to Van plus delta VBC, but delta VBC is anyway not in phase with your with phase A voltage, that is Van, right. So, in that case what will happen, that you go for a little bit the phasor diagram, right. So, before telling anything, you consider Van is your reference phasor, that is this one, Van is your reference phasor, this, right. Then if this is Van, this is Vbn and this is your Vcn, 120 degree phase shift, right. So, this is Vcn, that means this is Vnc, this is Vbn, resultant is Vbc. So, Vbc actually is lagging 90 degree from Van, right. Now, figure 27, this one, right. Now, this is your An. Now, figure 27, that is this one, give the phasor voltage phasor diagram. Now, let us assume that delta Vbc, that means this delta Vbc means this one, this impressed voltage which is in series with in this A phase, this winding is in series with this delta Vbc. So, this delta Vbc we assume it is equal to A into your Vbc, right. Delta Vbc is equal to A into Vbc, total is Vbc, but this is delta Vbc, this is actually from here to here, this is delta Vbc, right, this is delta Vbc. So, is A into your Vbc, A is some fraction, right. So, is equal to Vbc, actually Vbc lagging from Van by this thing 90 degree, and Vbc is line to line voltage, right, AB, BC, CL line to line voltage, they are √3 times the your what you call phase voltage, which is balanced system. So, we can write Vbc is equal to here √3 into Vn angle minus 90 degree. So, from this phasor diagram. So, this Vbc you substitute here, if you do so it will be A into √3 Van angle minus 90 degree. This is, that means delta Vbc is equal to, it is angle minus 90 degree, that means we can write minus j √3 Vn. So, delta Vbc is equal to minus j √3 Vn. This delta Vc expression you substitute here in equation 45, you substitute here, right. If you do so, you will get that Van dash is equal to 1 minus j √3 into Van. This is equation 47. That means, this Van dash actually it is minus j √3, a may be some fractional value, right, but then that means Van dash is lagging from Vn by an phase shifting angle alpha. So, Van and Van dash they are not in phase, but Van dash is lagging from Vn by angle alpha, right. Therefore, note that this injected voltage delta Vbc is in quadrature with the voltage Vn, and thus the resultant voltage Va dash n goes through a phase shift alpha as shown in figure 27, this one, right. Therefore, similar connections for your are made for the remaining phases also, because 3 phase balance. So, you have to make the same connection for the other 2 phases like B and C, right, resulting in a balanced 3 phase output voltage. Thank you.